So we can say a bit more than this. We can say that okay, so the point is we want to construct a spherical fibration. We kind of know what it should be. It should be the so the disk bundle of the fibration should look a bit like our normal neighborhood, and the spherical part should look a bit like the boundary. So this, as it stands, is not a fibration. So we use the path space construction to make it a fibration. So consider this. So I want to mention I'm borrowing quite heavily from Wolfgang Luck's explanation of this in his notes. So this is I to the minus, so this is the homotopy inverse. So I'm going to call this map F. So we want to take a path space fibration, path space construction to make a fibration to X, so that EF is homotopic to the boundary of the normal neighborhood. Okay, so just because this is a regular neighborhood, we have the homotopy extension property. So if we've got a homotopy on the boundary, we can extend it to the interior of the neighborhood. So in other words, it's a cofibration. So I want to say that this extends to a homotopy from the mapping cylinder. So what do I call this? What did I call this? So this was P, I think. So the mapping cylinder of P, EF, is now homotopic as pair to neighborhood of X, boundary in X. So I guess this is as boundary of NX inclusion into NX is cofibration. Okay, so we have our potential for the Tom class that lives in the cohomology of this pair. So under the homotopy, we can put it in the cohomology of this pair. So let's say HK, so I guess I'm making another claim about this Tom class, is that it's a generator, but I think this comes out of the commutative diagram. So HK of the so this is isomorphic to Z generated by, just calling it U. And then I'm going to say that transfers to, we should have some kind of Tom class like object, mapping cylinder relative to path space. So this is now generated by the push forward of this, which I'm going to call UP. So I guess we've got something that acts like a Tom class. We've got a fibration here, but the point is we don't know the fiber is homotopic to a sphere. And this is the main difficulty of this proof. This is where all the work in this proof goes in. And I have not read the proof. It's I was warned off it. It's yeah, uses a lot of quite heavy machinery. So I guess I will refer you to so e.g. Renitzky algebraic theory of surgery. For the completion of this proof. Okay, so how am I doing for time? Okay, so the property of having a Spivak normal fibration completely characterizes Poincare complexes. So I guess the natural question is, why is this important? So it allows us to, in a different language, say when we have overcome the first obstruction to a CW complex being a manifold, which means we can start talking about the next obstruction. So I guess this is section 4, consequences. So I'm going to start off with a theorem, which I guess is sort of the main point of all the surgery stuff we're going to be doing. So this is Browder 62. So a P-space so a simply connected P-space is homotopy equivalent to a manifold, say M, where I guess this is the homotopy equivalence, if and only if. So there exists a vector bundle, so by now this should look quite familiar. So this is the vector bundle, and some map to Tom space, so such that our agreement with the Tom isomorphism from before holds. So this is fine. This is all you need in odd dimensions. So note this is a vector bundle. And then the second condition. So if M is even, we have a couple more conditions. So if M is 4K, there's a condition on the signature, which is that. So the signature of the Poincare complex should be so that's if M is 4K, and if it's even and M is 4K plus 2, we're getting this condition on the self-intersection. So this is so the Z2 valued ARF invariant, whatever that is, so I guess we'll talk about that in a bit, of the self-intersection form. So I believe Philip talked about this. Mu, so remember mu is a form that goes from the kernel of, so I guess F is our map here, so F star of the, do I mean this? Yeah, I think I mean this. So 2K plus 1, a manifold, Z2 to itself, let's just say to itself, and that goes to Z2. Vanishes. So now we've got a complete characterization of what a P-space is. We can start to check the next properties. And in fact, the first vector bundle property is going to be is sort of well stated in the language of Spivak normal bundles, right? Okay, so recall we had the map that forgot the vector bundle structure. So that takes a stable normal bundle, well, in our case it takes a stable normal bundle to the associated Spivak normal fibration. So the point is, these are exactly the same conditions as on a Spivak normal fibration, so we want to lift the map. So this is the Spivak normal fibration. So we want to lift the map there. So we can define the co-fiber. Did I mean co-fiber? No, the fast fiber. So we can define the mapping fiber. So this is going to be, no it's not, it's going to be, so G of O is the mapping fiber that makes this a fibration sequence. So let's say define G of O to be the mapping fiber. And then we can extend this to the right, it turns out, because this is a monode, to get B G over O. So in fact, the obstruction to the lift, so let's call that lift, obstruction to mu x twiddle,